Hello everybody and welcome to our video on derivatives and the shapes of graphs. So what we're going to start with here is looking at the relationship between derivatives and whether a graph is increasing or decreasing. Now, we should already have some intuition about this. We know that a derivative means the rate of change of the function, and so intuitively, if you say the rate of change of something is positive, that should make you think it's increasing. And if you say the rate of change of something is negative, then that something should be decreasing. So of course, we're going to, formalize that a little bit more here. First, we start with the increasing-decreasing test. So if f prime of x is greater than 0 on an interval, then f is increasing on that interval. And if f prime of x is less than 0 on an interval, then f is decreasing on that interval. Okay, so again, that's just exactly that intuitive statement we just said. But let's try to sketch out a rough proof to make it a little more rigorous. So we know that the mean value theorem says that f of b minus f of a. Yeah, let me just get a draw here. F of b minus f of a divided by b minus a equals f prime of c for some c in the interval from a to b, assuming that f is differentiable and continuous on the interval, so forth and so on. So that's what the mean value theorem says, and of course you can always multiply this denominator b minus a across, and you'll get an equivalent statement. So here we're looking at the mean value theorem. What happens if we assume that x2 is greater than x1 and apply the mean value theorem? Then you get f of x2 minus f of x1 equals f prime of c times x2 minus x1. Now, of course, if we assume that the derivative is positive, so here this part of the proof is just for part A. We're just sketching out part A. Well, if we assume that the derivative is positive, then the derivative times x2 minus x1 is also positive, and so f of x2 minus f of x1 is positive, since they are equal. And of course, if f of x2 minus f of x1 is positive, then f of x2 is greater than f of x1. So in other words, f is increasing. For part B, it's basically the same, right? All you do is just flip around that it would be negative instead of positive at the end, and so you would get that f of x2 was less than f of x1. Okay, so let's move on. Let's sketch the graph of a function that satisfies the following properties. So the first property, f prime of x is greater than 0 for x between negative infinity and 2. And one of the things that I always want you to do when you're working on problems like this is translate them. F prime is positive, so write f is increasing here. And here, f prime is negative, so we translate that to f is decreasing. And here, f is increasing again. All right, f prime is positive. Now, each of these is on a different domain, right? This is negative infinity to 2. This is 2 to 4. This is 4 to infinity, right? And also we have two other conditions. F prime of 2 is 0, and f prime of 4 does not exist. So when you're trying to draw one of these types of graphs, the first thing that I want you to do is label below your graph what's happening in terms of increasing and decreasing properties. So what do I mean by that? I mean, this says from negative infinity to x to, for x from negative infinity to 2. So that means everywhere from 2 backwards, the graph is increasing. And so I'm going to notate increasing by just putting a little up arrow here on this part of the interval. And then from 2 to 4, our properties tell us that the function is decreasing. So I'm going to put a little down arrow here. And from 4 onward, it says f is increasing again, so a little up arrow. And that's going to help when I'm drawing my picture, make sure that I'm drawing my picture doing that behavior on the appropriate intervals. Now, it also says f prime of 2 is 0 and f prime of 4 does not exist. It doesn't tell me where to plot these points, so I can plot them wherever I want, but this at 2, I need a tangent line that's 0. So I'm going to plot it up here, a horizontal tangent line. And f prime of 4 does not exist means there should be a corner or a cusp or something like that. And since over the interval from 2 to 4 the graph is going down, I'm going to plot whatever point at 4 happens, I'm going to plot it below hand. So we'll put like a corner right there. And now, again, the graph is increasing all the way until 2, so I'll just draw something like that. And then it decreases down to here. And then it increases again for the rest of the interval. And that looks good to me. Okay, moving on. So now we'll talk about the first derivative test. The first derivative test is just a test to determine whether or not a critical number corresponds to a maximum or minimum for a function, a local maximum or minimum. So recall that a critical number is a place where the derivative is either 0 or doesn't exist. So this theorem says if f prime changes from positive to negative at a critical number c, then f has a local max at c. So that's these first two cases here. We've got 2, we've got the derivative is 0 or the derivative doesn't exist at c, right? But in both of these pictures, we've got a derivative that's positive. Our slopes of our tangent lines are positive. Then they hit 0, and then they become negative. And here again, the slopes of the tangent lines are positive, then it doesn't exist, and then they're negative. So in both of these cases, we have a local maximum. Now, if we look at part B of this theorem, it says if f prime changes from negative to positive at c, then f has a local minimum at c. So again, we take a look at our pictures here, and we go, okay, well here, this one, the derivative is 0. This one, the derivative at c doesn't exist. In both cases, our derivatives are negative beforehand and positive after. Negative, then positive. And in both cases, we see that these points, f of c, corresponds to local minimums. And c, if f prime does not change sign at c, then f has no local maximum or minimum at c. So we look at y equals x cubed as an example. So we've got the x cubed function. We know its derivative, y prime, is 3x squared. And so we know that y prime is 0 when x equals 0, right? So this is just to point out that, hey, we know that there are functions that we work with that do this. This is a specific example. And in this function, the derivative at 0 is 0, but the derivative goes from being positive to positive again. And so we don't actually get a maximum or minimum. The graph just kind of levels off and then goes back up again, but doesn't give us an actual maximum or minimum value. Okay, so let's go ahead and take a look at an example and apply these two ideas. For f of x equal to 2x squared minus 8x plus 3, a, find the intervals of increase or decrease, b, find and verify the local minimum and maximum values, and c, sketch a graph of f of x. Okay, all of these things are going to require that we take the derivative. So I'm going to start out by taking the derivative off to the side here. F prime of x is 4x minus 8. Pretty easy derivative. Now, the first thing I want to do is find my critical numbers. Find where the derivative is 0 or doesn't exist. Well, this is a polynomial, so the derivative always exists. So all I have to worry about in this case is where this thing is 0. So we get 4x equals 8. So x equals 2. All right, remember that's where f prime is 0 here. Okay, so now we want to find out where the function is increasing or decreasing. And so I'm going to plot a number line here, and we're just going to notate this number line the same way we do our graph from earlier, right? The same way we labeled this graph, increasing, decreasing, increasing. We're going to do that same kind of label here, but we have to check some points. This is the key thing. We know that our graph, the derivative at 2, f prime is 0. And way back in the beginning of the course, there's a theorem that says the intermediate value theorem. And essentially it says that if a function is going to hit 0, or if a function goes from negative to positive or positive to negative, it hits 0 somewhere in between. So in other words, the only time that a function can change from increasing to decreasing or vice versa is whenever the derivative is 0. Everywhere else, the interval is going to stay the same sign. So here's what I mean by that. All I need to test is a single point on each of the intervals here. We've got from 2 to infinity and 2 to negative infinity. So I'm going to test 3. That gives me a point on the right side. And when I take the derivative at 3, I get 12 minus 8 is 4. That tells me that on the right side of my interval, f prime is positive. And so I'm going to draw my little up arrow here. And when I take the derivative at some point to the left of 2, we'll just pick 1 because it's easy. You could pick any point you want on the interval to the left of 2, any point you want. I'm just going to pick 1 because it's the easiest point I can think of. I mean, 0 is pretty easy too, but that's fine. Okay, so 1 is 4 minus 8. That's negative 4. So here we get that f prime is negative. And so we draw our little arrow going down. And now we'll summarize that information by actually specifying the intervals. So what does this tell us? F is increasing when, well, let's just say we'll do it in interval notation. Increasing on the interval from 2 to infinity. And f is decreasing on negative infinity to 2. And that's it, right? So again, the point here is, I want to make this as clear as possible. Once I know the critical numbers, those are the only places where the function could change from increasing to decreasing or the other way around. So all I have to check is on either side, on any of the sub-intervals here. In this case, our critical number only breaks this into 2 intervals. So I only have to check 1 point to the right of 2 and 1 point to the left of 2. I picked 3 and 1. And that's it. Plug them into your derivative, see if it's increasing or decreasing. Okay, so now we'll look at part B here. It says find and verify the local minimum and maximum values. All right, so since f prime goes from negative to positive at x equals 2, that implies that f of 2, which is 2 times 4 minus 8 times 2 plus 3, that's 8 minus 16, that's negative 8 plus 3, that's negative 5, is a local minimum. And if you can't recall the theorem, well, that's okay, because just think about the picture. The derivative goes from negative to positive, so the graph is going down and then up. So what's going to happen in between? You're going to be at a minimum, right? So that's why I want you all to always draw this label or this interval label, so that it makes it easier to tie all these things together between the derivative changing from negative to positive and there being a local minimum there, etc. Okay, so sketch a graph of f of x. So first of all, we know there's a local minimum at 2, -5. And what else do we know? We know that this function is decreasing and then increasing on either side of that interval. And what else? Well, that's really enough, but I'll plot just x equals 0. Let's see, when x equals 0, you get 3. So we'll just plot one other point. I don't want people plotting a million points to graph these things. That defeats the purpose. But I do know that this is a quadratic, so I know that if I know the 1/2 of the side of this, I know the other half is going to be a mirror image. So just shoot that up there, and boom, that's my graph. Okay, so let's move on, and now we'll address another related topic, which is that of concavity. So the rigorous definitions for concavity are as follows. If the graph of f lies above all of its tangent lines on an interval I, then it is called concave upward on I. If the graph of f lies below all of its tangents on an interval I, then it is called concave downward on I. Now, intuitively, how we think of this is concave up is shaped like a cup up, right? So this picture on the left, it's like the curvature of a cup facing upwards, and concave down is like the curvature of a cup facing downwards. And that's it. That's the whole idea. But the rigorous definition does give us some ability to do some other analysis, like if I know that something is concave up, so take, for example, this picture here. If it's concave up, that tells me that the tangent line approximations are an underestimate for the function, whereas if it's concave down, that tells me the tangent line approximations are an overestimate. So these rigorous definitions give us some more information about the function that's useful, but intuitively you can just think, hey, concave up is like a cup up, concave down is like a cup down. Okay, so definition, a point P on a curve y equals f of x is called an inflection point. If f is continuous there, that's important, continuous there, and the curve changes from concave up to concave down, or vice versa at that point. So in other words, if I have something like this, looks like a cup down, and then at this point it looks like a cup up, this is called an inflection point, wherever the concavity changes. Okay, now how do we test concavity on a function? Well, it's simple enough. If the second derivative is positive, then the graph of f is concave up on that interval. If the second derivative is negative on an interval, then the graph of f is concave down on that interval. Okay, why? That's always the critical question. Why? Well, if f double prime of x is greater than 0, then f prime is increasing on I. F double prime of x is greater than 0 means that f prime is increasing on I. And if f prime is increasing on I, that means the slopes of the tangent lines are getting steeper. So try to picture what's happening here on this graph. As the graph moves to the right, the tangent lines curve upward, and so the slope, the curvature of the graph forms a cup facing up. On the other hand, if the second derivative is negative for all x and I, then f prime is decreasing on I. So, in other words, the tangent slopes are getting smaller. The slopes are smaller, and so the shape that it carves out on our graph is something that is facing down, a cup facing down. Now, before we move on, I just want to kind of summarize a lot of this information because there's a whole lot of stuff going on in this section, but it's really about tying a bunch of things that we mostly already know together. So let's just summarize this off to the side as equivalent statements. And these are going to be really, really important to be able to change in between comfortably, to be comfortable in going, okay, these things are all equivalent to one another, and you should be able to move fluidly between them. So let's start here. F is concave up. If and only if F prime is increasing, which happens if and only if F double prime is positive. This is the first one. All three of these statements are equivalent. F is concave up is the same thing as saying F prime is increasing, is the same thing as saying F double prime is positive. They're all the same thing. On the other hand, F is concave down. If and only if F prime is decreasing. If and only if F double prime is negative. So again, all three of these statements are equivalent. F is concave down is the same as F prime is decreasing is the same as F double prime is negative. They are all equivalent statements. Additionally, just to summarize earlier, F is increasing if and only if F prime is positive, and F is decreasing if and only if F prime is negative. Okay, so that's the summary of everything about increasing, decreasing, and concavity in terms of how a function and its derivatives relate. All right, so let's move on and let's sketch a graph. So sketch the graph of a continuous function that satisfies F double prime is positive for x less than 1, and F double prime is negative for x greater than 1. And as before, the first thing you should do is translate this. F double prime is positive. What does that mean? Oh yeah, that means F is concave up. And F double prime is negative means, oh yeah, F is concave down. So now when I go to sketch my graph, the first thing I'm going to do is I'm going to label intervals at the bottom just like before. So the breakpoint here is at x equals 1. And so for x greater than 1, it's concave down. So I'll label this with a cup down. And for x less than 1, this first condition said it was concave up. So we'll label it with a cup facing up. And so at 1, it has to change concavity, like that. And so there, that's a graph that does exactly what was asked. All right, so now we'll talk about another way of looking at, or I should say verifying, whether a function has a local maximum or a local minimum at a point. So this is called the second derivative test. Suppose F double prime is continuous near C. If F prime of C is 0 and F double prime of C is positive, then F has a local minimum at C. If F prime of C is 0 and F double prime of C is negative, then F has a local maximum at C. And the test is inconclusive if F double prime of C is 0. So if we look at case A, well, actually, yeah, look at case A. That's actually the one in the middle here. Maybe I should have labeled those differently. That's the middle case. The second derivative is positive. that means we've got a cup facing up, and that means that this point at C had to have been a minimum because the graph is cupped up away from that point. And if we look at B, that's really this first graph here. So f double prime is negative, so it's concave down, it's a cup facing down, and that tells you that at C, this point must have been a maximum. If the second derivative is 0, then the test is inconclusive. And again, we come back to that example of y equals x cubed. So y prime is 3x squared. So y double prime is 6x. So the second derivative is 0 when x equals 0. But in this case, it has neither a local minimum or maximum. That's not necessarily true. But it is true that if the second derivative is 0, we can't say anything based on the second derivative test. Okay, so now let's go back to that same function we dealt with before, but now we're going to find the intervals of concavity and the inflection points, and then we're going to verify the local extreme value using the second derivative test instead. So, if I want the intervals of concavity and the inflection points, we start by taking some derivatives. I get 4x minus 8. And then when I take my second derivative, I just get 4. And 4 is strictly positive, so this implies that f is concave up everywhere. That second derivative is always positive, so this function is always concave up. Now, f prime of 2 is 0. We saw that before when we dealt with this function. And f double prime of 2 is 4, because f double prime is always 4. So f double prime is positive. So if the first derivative is 0 and the second derivative is positive, that implies that f of 2, and what was f of 2? Negative 5. I don't really feel like recomputing it, so I'm just going to check. Yeah, that was right. Negative 5. Negative 5 here is a local minimum by the second derivative test. And again, the first derivative is 0, the second derivative is positive. That means it's concave up. And that means, all right, concave up means that the point is at the bottom of that cup, so it's a local minimum. All right. So now let's look at the combinations of increasing and decreasing with concavity. So just so you can see all the shapes that you're looking for when combining these two types of information. So this first one is a picture of something that's both increasing and concave down. The next one is something that's both increasing and concave up. This one is decreasing and concave down. And this one is decreasing and concave up. So you see, you can combine all of these in any combination. And it's just going to change how you draw that part of the graph. All right, let's take a look at this example. So here we've got f of x equals 24x plus 9x squared minus 2x cubed. And we want to find the intervals of increase and decrease, the intervals of concavity, any local extrema, and then graph the function. So in order to find the intervals of increase and decrease and the local extrema, we'll have to start by finding the first derivative. So let's go ahead and do that. All right, so f prime of x will be 24 plus 18x minus 6x squared. And if I want to find out where this derivative is 0, I'm going to need to factor it. And the easiest way to do that in this case is to first factor out the negative 6 here. So I pull out the negative 6. This term will be a positive x squared. And the 18x will become a negative 3x. And the 24 will become a negative 4. And now to factor this quadratic, I need factors of -4 that add up to -3. So that's going to be -4 and +1. So if I set this derivative equal to 0, what x values will I get? Well, it's got to be x equals 4 or x equals -1. Okay, so for our intervals of increase and decrease, let's go ahead and draw our number line. So we're concerned with what happens on each of the intervals around -1 and 4. And so now we just need to plug into our derivatives some x values in these intervals. So remember, we know that the derivative is 0 at -1 and 4. And so we know it's on any of the other intervals between or on either side here that the derivative has to stay the same sign, whether it's positive or negative. So I'll just pick one value. How about -2 to test the derivative? And we'll plug into this factored form. I think that's a little quicker to compute. -6. -2 minus 4, that's going to be -6 again. And then -2 plus 1, that's going to be -1. 3 negatives makes a negative, so this will be -36. So we get that f prime is negative here, and graphically that means the function is going down on that interval. And now we'll evaluate f prime at, well, 0 is in the next interval from -1 to 4. So we'll evaluate f prime at 0. And that's actually easier to plug into the original version for f prime. We just get 24. So here we get f prime is positive, and so the graph is going up. And now we'll evaluate f prime at, let's go with 5. And again, I'll plug into the factored form. That's -6 times 1 times 6. That's -36. And so again, we get that the derivative here is negative, and so the graph would be decreasing. Okay, so to properly answer the question in part A, f is increasing on the interval from -1 to 4, and decreasing on the interval from -infinity to -1, and unioned with the interval from 4 to infinity. All right, so now let's move on to part B. And for part B, I'm going to need the second derivative. And of course, the easiest way to get the second derivative is to start with this polynomial form for the first derivative, the first way we'd written it. Derivative of 24 is 0. So derivative of 18x is 18 minus 12x. In order to find the intervals of concavity, I first need to check where the second derivative is 0 or doesn't exist. Of course, this exists everywhere. But if the derivative is 0, then 18 minus 12x is 0. So the second derivative is 0, 18 minus 12x is 0. That implies 18 equals 12x. If I divide the 12 and simplify, I'll get 3 halves. X equals 3 halves. Okay, and so I'll draw my interval here. And now we just need to check our second derivative at a point on either side of 3 halves. So we'll start with, how about f double prime at 0? That's a nice easy one. That's going to be 18. So that tells us that f double prime is positive on that interval. And if f double prime is positive, we get concave up. And now we'll check f double prime at 2. If I plug in 2 into 18 minus 12x, that'll be 18 minus 24, that's negative 6. So we get f double prime is negative. And therefore the function is concave down on that interval. Okay, so let's write that properly. F is concave up on the interval from negative infinity to 3/2, and down on the interval from 3/2 to infinity. Okay, so now we need to find the local extrema, and we can do that just by looking at our results from the decreasing test. So if we look at the place where the derivative is 0, doesn't exist, if we look at the first one, -1, we're going from decreasing to increasing, which tells us there's a local minimum here. So f of -1, and we do need to plug that in and evaluate it. So that's going to be -24 plus 9 plus, that's, that'll be -2 times a -1. That's going to be a +2. So that's going to be -13. And this is a local minimum. On the other hand, if we look at f of 4, at 4, the function is going from increasing to decreasing. So that's going to be a local maximum. And if we try to plug in 4 into our function, let's just zoom out a little bit so I can get the whole thing on screen here. We get 24 times 4. It's going to be 96 plus 9 times 16. That's 144. Minus 2 times 64. So let's see, 64, 2 times 64, 128. So minus 128. Okay, and what does that leave us with? That should be 112. All right. Now our last task is just to graph the function. So what we're going to do is lay out our graph, and we're going to go all the way from -1 to 4 as far as points that we're key parts of the graph we're looking at. So we'll have -1 here, 4, and 3/2 is also. Okay. And we can plot our local minimum and local maximum. Well, before I do that, let me go ahead and just draw my little breakdown here. Okay, so this just makes it easier to visualize. We know we're decreasing, then increasing, then decreasing. So our graph goes down, up, down on those intervals. And then we know at 3/2, we go from concave up to concave down. Okay, so now we'll plot our 2 points. I probably should have gave myself a little bit more room. Bear with me here for just a minute. So this is not going to exactly be to scale because obviously we're going up to 112 here. So we're just going to mark on the y-axis here. This will be our negative 13. And up here, this will be our 112. And f of 4 is 112, so we'll plot that point up there. And f of negative 1 is the negative 13, so we'll plot that down here. And now, the graph is decreasing until it gets to negative 13, then increasing, and it's concave up this whole time. And just to make sure the graph is reasonable, when x is 0, we get 0 for f. So just make sure it passes through at a reasonable point on the y-axis. And it's going to keep increasing, but it's going to change concavity when x is 3/2. So it should be concave up this whole time. And then it's going to switch to concave down. And it's going to keep increasing to this point, and then it's going to start decreasing. And there we go. As long as your graph looks something reasonably like that, I'm pretty happy with it. Okay, let's take a look at another example here. Example 6, sketch a graph that satisfies the following conditions. F prime is greater than 0 if the absolute value of x is less than 2. F prime is less than 0 if the absolute value of x is greater than 2. F prime of 2 is 0. The limit as x goes to infinity of f of x is 1. F of negative x is negative f of x. F double prime is negative if x is between 0 and 3. And f double prime is positive for x greater than 3. So whenever we're given explicit conditions like this and we need to graph them, I think it's always best for students to first translate the function properties into the terminology about the graph to make it a little easier to figure out. So I look here, I say f prime of x is positive. That means the function is increasing. So we have f is increasing. And if the absolute value of x is less than 2, that means x is between negative 2 and 2. And f prime is negative, means f is decreasing. If the absolute value of x is bigger than 2. That means all of the cases that aren't covered by x being between negative 2 and 2. So in other words, when x is bigger than 2 or x is less than negative 2. F prime of 2 is 0. This means a horizontal tangent at x equals 2. The limit as x goes to infinity of f of x is 1, means a horizontal asymptote at y equals 1, and specifically on the right side of the graph, because x is approaching positive infinity. F of negative x equals negative f of x is symmetry about the origin. And you may recall that that means a reflection over, or around, I should say, the origin. F double prime is negative. That means the function is concave down. on the interval from 0 to 3. And if f double prime is positive, that means concave up on the interval for x greater than 3. All right, now to keep some of these things on screen, we'll zoom out here a little bit while I start setting up the graph. Okay, so first I want to set up my markers for increasing and decreasing. So that's going to change at -2 and 2. So if I draw an interval here, from -2 to 2, this thing should be increasing. And it should be decreasing otherwise. So down on these intervals. Okay, so I'm going to cross off things as we go. We did those two. Now, as far as drawing the horizontal tangent at x equals 2, we'll worry about that at the end. So first, I'm just marking under my graph to get a good idea of what things are going to look like. So now we'll do concavity here. And so for concavity, it only tells us what the concavity looks like on the right side of the graph. So from 0 to 3, we're told it's concave down, and from 3 onward, it's concave up. But we do have the symmetry, and we also have this horizontal asymptote. So that says that the y value approaches 1 as x goes to the right. Okay, so now all we have to make sure is that we follow the increasing decreasing pattern. We're going to draw the right side of the graph only, since we only know the concavity there, and then we'll figure out how to deal with the left side of the graph. And we also need to make sure we have a horizontal asymptote at, a horizontal tangent at x equals 2. So here we're increasing from 0 to 2. And then we're decreasing. So we need to be above this tangent line so that the function can decrease towards that tangent line. And it also needs to be concave up starting from x equal to 3 onward. So it's concave up here, and then it should be concave down on this interval. Now I drew this going through the origin because I know that there's the symmetry where it's rotated around the origin, and the easiest way to draw that, it would be with a continuous function that goes through 0, 0. Now, since this thing should be a reflection about the origin, all you have to do at this point is just draw a rotated mirror image of your graph. It's not perfect, but close enough. We're going to go ahead and go through one more problem here. Let's just jump right in. So for f of x, or f of theta equal to theta minus sine of theta on the interval from 0 to 4 pi, A, find the intervals of increase and decrease. So let's start by taking our derivative, f prime of theta. That's just 1 minus cosine of theta. So when is f prime of theta 0? That's when 1 is equal to cosine of theta. Okay, well, when is cosine of theta equal to 1? Well, hopefully we remember our unit circle, and we go, well, 0 and 2 pi and 4 pi. Remember, we're only looking at the interval from 0 to 4 pi here, so we don't have to think about all possible answers. So now we want to find our intervals of increase and decrease. So well, let's go ahead and plot our interval here. Well, in this case, the interval doesn't go on forever, right? It stops at 4 pi and 0. So we'll put 2 pi right in the middle there. And so what is f prime of? Well, we need to pick something in between each of these zeros for our derivative, right? And so we'll take f prime of pi. And f prime of pi is 1 minus -1, which is 2. So that's positive. So we'd say f prime is positive here. So the graph is going up. And when we take, let's say, our first derivative at 3 pi, we get the same thing. Cosine is still -1 at 3 pi. So we still get 2. So f prime is positive. So the function is still increasing here. Okay, that's part A. About part B, find the local and absolute extrema. Well, here, look, what do we notice? F prime does not change sign. Right? It stays positive the whole time, so there are no local extrema. On the other hand, if we want to check for absolute extrema, we need to check the endpoint values. So f of 0, that's 0 minus sine of 0, which is also 0. So that's 0. And f of 4 pi, that's 4 pi minus sine of 4 pi. And sine of 4 pi is 0, so this is just 4 pi. So that tells me that 0 is the absolute minimum, and 4 pi is the absolute maximum. Okay, so now we can move on to part C, find the intervals of concavity and the inflection points. Okay, well, for concavity, we of course need our second derivative. So we take the second derivative at theta. Derivative of 1 is 0. Derivative of cosine is negative sine, so this is a negative sign. In other words, positive sine of theta. And when is the second derivative 0? When sine of theta is 0. And when is sine of theta 0? Well, sine of theta is 0 at 0, and pi, and 2 pi, and 3 pi, and 4 pi. So we draw our interval. And now we start checking our second derivative at some points inside each interval. So at pi over 2, what do we get? We get sine of pi over 2, which is 1. So this is positive. And then f double prime of 3 pi over 2. That's -1, so this is negative. F double prime of, the next one would be 5 pi over 2, is going to be positive again, +1. And f double prime of 7 pi over 2 is going to be -1 again. And so f is concave up on the interval from 0 to pi, union 2 pi to 3 pi, and down on the interval from pi to 2 pi, union with 3 pi to 4 pi. Okay. Now we've got our concavity, so we can label this with our little cup signs. And now we could start to graph our function. Except I forgot one thing. We're supposed to also find the inflection points. So where does the graph change concavity? Well, we don't consider the endpoints here because we don't know what happens on either side. So we're only looking at pi, 2 pi, and 3 pi. And so f of pi, which is pi minus sine of pi, and sine of pi is 0, so this is just pi. So the point pi pi is an inflection point. Okay, what else? F of 2 pi. Well, that gives me 2 pi minus sine of 2 pi. And sine of 2 pi is 0 again, so this is just 2 pi. And finally, f of 3 pi. 3 pi minus sine of 3 pi. Sine of 3 pi is 0 again, so this is just 3 pi. So in other words, the points pi pi, 2 pi 2 pi, and 3 pi 3 pi are all inflection points. Try saying that 10 times fast. Okay. Those are our inflection points. So now we have absolute max and minimums. We have inflection points. So we're going to graph our absolute max and minimums. We're going to graph our inflection points. And we're going to graph our increasing, decreasing properties. So the first thing is to sketch out my graph. We're going from 0 to 4 pi. And our maximum value of our function was 4 pi. And we're hitting all of the pi's in between for our inflection points. Okay. And now let's label increasing and decreasing. So the split is at 2 pi, but it's really just increasing the whole time. So it's really just going up the whole time, but there's a little moment where the derivative is 0 at 2 pi, so we know there should be a horizontal tangent here. All right, we did see that the derivative was 0 at 2 pi, so horizontal tangent there. Okay, and what else? We know that this thing is alternating between concave up and down every pi. And so we started up, down, up, down. So up, down. And that should be enough to graph our graph pretty satisfactorily. So I'm going concave up, but increasing. And then it's going to become concave down, but still increasing. And then concave up. And then concave down. And there's our graph. Okay, I know that was a bit of a long one, but thank you for sticking through it, and have a great day.